Okay, let's get started. Can I get a couple of thumbs up if you all can hear me? I'm trying to get everything reset back up after a week out. Cool, I'm seeing some thumbs up, so it looks like we're pretty good to go. Cool, hey everybody. So today we're going to talk about object-oriented programming and data pipelines. The Slack has the lesson we'll be working through, so make sure that you've forked that, you've cloned it down, and that you've created a new branch on your local machine. For those of you who have done some programming before, maybe in a different language, a lot of this might feel a little bit familiar. For those of you who have, this is your first time ever using programming or doing coding work or Python, this is going to be kind of hopefully mind-blowing and sort of expansive. And we're going to kind of really spend the first hour or so today talking about like the actual guts of Python and why things work the way they do in this specific language. And we'll talk about how that gets applied to something known as a data pipeline. And pipelines are very cool. I'm actually super excited to talk about them. They're my favorite part about the scikit-learn library. But let's hop over here. I'll switch my screen over real quick. There we go. So this is the sort of lesson that we're going to be working through today. And this is Intro to Object-Oriented Programming. And by the end of this lesson, you'll be able to tell me we'll define what this object-oriented programming thing is. You'll be able to identify what a class is in Python and sort of classes that you may have used in the past. We've already made use of a bunch of different classes. And so this is going to be a good way to kind of look back and say, like, OK, now I understand why things are happening the way that they are. We'll talk about this concept known as inheritance and why it's helpful for classes. We'll talk about this concept of self and how it relates to those classes. And then in this sort of latter half of the class, we'll talk about what data pipelines are, why they're useful, and then these pipeline and feature union sklearn objects to help us create these data pipelines. Inside this lesson is a Jupyter notebook that we'll be working through, but also the solution codes. So don't worry too much if you need to like sort of fall back and look at that solution code as well. Everything that we're going to type through or that we're going to have answers to is already up there on that Slack or on that GitHub. So without any other further ado, let's sort of get started. I'm going to hop over into that notebook. So that's going to be, let's click through here real quick. So I'm going to go to my J folder, DSI East folder, into my lessons, Intro to OOP Data Pipelines. And I'm just going to go ahead and run this intro notebook. And the first thing you'll notice is that we have a huge amount of imports. So we're just going to run this. I've sort of tried to do my best to make sure that all these imports are sort of split up by module, but we'll see a lot of different cases where these sort of carry through. Frank in Atlanta says we need more imports, and I would tell him, do not worry, there will be more imports. So cool. So let's talk a little bit through about like what this intro to object-oriented programming stuff looks like. And in Python, everything is known as this sort of object. This is what the basis of like an object-oriented programming language is. And broadly, what an OOP language does. So to sort of set the scene, within programming languages, we sort of have two different paradigms working at the same time, object-oriented and functional. And Python is a very interesting language in that it is, at its core, object-oriented, but it can do a lot of the same things that a functional programming language can do. We'll sort of see some examples of both in a little bit. But within an object-oriented programming language like Python, our focus is going to be on what these objects can do and how to modify them. So for some examples, let me zoom in here a little bit to make this a little clearer. Oops, I have zoomed in on my Slack instead. There we go. Perfect. So some things we might want to do, right, is we have a list object. So a list, we can add all the things up inside a list. We can sum up those objects. We can take the average of them. We can take elements out. We can sort of iterate through those things. And these are all things that we're doing to a object, right, to something called a list object. And within a pandas data frame, it's the same sort of concept. We can slice. We can change the values in the columns. We can move them to a new data frame. We can reduce them. So we can take aggregate statistics, the average, the mean, the median, the mode. We can do a whole bunch of different things with that actual object that exists, right? So there's some sort of thing in memory that says, I am this data frame. Things you do to me, I'm going to hold on to and keep track of. And stuff like a decision tree classifier, right, which I think you all covered last week, same exact sort of concept. we're gonna have this sort of decision tree object. Once we fit it, we'll have like sort of splits at these nodes. We'll be able to look at them. We'll be able to take new data and refit them or reprogram them. We'll be able to use those values that they've stored to predict new data or score new data. And so the sort of kind of key concept here, the thing that we're sort of repeating over and over again, is that we have something that we have, and we're doing things to it. We're modifying it, we're changing it, we're viewing it, we're doing things to these objects. And the core of our focus has been on these objects. And some things that are common across these objects, and broadly this sort of this programming paradigm, is that we've defined everything in this language about things that they can do and that they can't do, right? So there's an inherent behavior that every object has that other objects might not have. So one way to think about this is to consider, a string and a float, right? A float I can divide by 2. I can take the average of a string. I can go ahead and index out a certain character or a certain index value. I can concatenate it with another string. I can turn it uppercase. I can turn it lowercase. But strings can go uppercase and lowercase. Floats can't. Floats can take the average of themselves or sum them up or divide them by 2, and strings can't do those things. So inherently, each of these objects has a different thing that they can do and that they can't do. And so number 2, right? So that's the first part about this sort of programming paradigm of object-oriented programming, which is things have certain inherent behaviors. Secondly, one of the things that is really important is that every object here is mutable, right? We can change them, we can add them, we can modify them, right? I can take the string hello Richard and I can add on Harris to it. I can take the float 2.0 and I can add 4.0 to it. So these objects are mutable, right? They have certain things they can and can't do, but we can change what they are pretty quickly. And our focus, and number 3, right, the thing that sort of defines this object-oriented programming paradigm, is that our focus as developers in a language like this, in an OOP language, is that we want to know what we can do to each of these objects and how to connect them, how to modify them, how to destroy them, how to make them do the things we want them to do at that point. So our focus really is going to be, here are objects, what are the behaviors that they have built into them, and how am I going to use those behaviors to modify certain values or certain things that are stored in there, right? I think you all covered like web scraping and web development in a pretty good amount of detail last week, but within Python, right, we have this web framework known as Django, and in Django you'll have these sort of things that are like user models or blog post models or address book models, right? And so every entry or every callback to that database to come back comes back as its own object. And you can filter on those objects, you can sum those objects, you can rank order those objects. Same sort of concept, right? We're going to rely on this idea of I've got a thing X can do fit, predict, score, fit, predict, and I'm going to use those methods to make things happen. I see a couple of questions sort of trickling in on the Slack. Definitely go ahead and put those questions in as you have them, and we'll sort of like work through that. So Kelvin is asking, Django, is that a framework? Yeah, so if you've ever heard of Ruby on Rails or some of the other web frameworks, Django is just a Python version of it. And it relies on sort of creating objects, and we're not going to go too deep into it, but definitely an interesting way to consider programming. Cool. So let's talk about the other side of this, right, which is this idea of functional programming. So in functional programming, right, our focus is going to be, as it says in the tin, is going to be on that function. In other words, here's something, and what are we going to do to it? So typically within functional programming, our data is going to be immutable, right? I'm going to set up something that holds my data, and it's not going to change. What we're going to do instead is we're going to pass that immutable, unchangeable object through a bunch of things so that the result of it is represented in a different way, right? The underlying data hasn't changed. It's just how we've represented it and that sort of thing. So, so we're going to use functions, we're going to use control flow, and the sort of end representation of the data will be different, but reproducibly different, right? We can send it right back through again and get the same thing. We can change one of the steps in the process and get a different result, but we're not changing that underlying data. So this is sort of conceptually, in some sense, like taking a CSV and putting it into a pandas data frame. That CSV doesn't change, but that process of going from CSV to data frame has now put it into a different representation. So in other words, right, kind of really broadly, and we're skipping through a lot of sort of the the computer science guts of this, because we're in a 12-week job skills course and we've only got so much time. But very broadly, right, these OOP sort of dynamics or paradigms are interested in looking at how we change objects. Whereas FP, or sort of functional programming languages, are interested in looking at how functions evaluate things. Most languages don't purely go one direction or the other. In fact, lots of them offer elements of both of them. Right? So Python has a strong object-oriented slant, but lots of people do a lot of functional programming in Python. And that's fine, right? It's less about, this is not a sort of hardcore dogmatic purpose insofar as it is sort of, how do you think about how you structure your code? What are the questions you ask? How do you approach a problem? So there are a couple other popular data science languages, right? R and Julia. R is a little bit older, Julia is a little bit newer. They typically have stronger functional programming elements than Python will have. So if you're kind of interested in exploring some of that stuff, we'll talk a little bit. We'll show a couple of examples of what functional programming looks like. But R, Julia, Clojure, Scala, these are all like good sort of data science languages that are more sort of functionally focused. And you in this class will actually get the chance to learn a little bit of Scala as well when we get into our big data section, because big data relies on stuff like that. But let's take a peek at this example. So if I wanted to do sort of object-oriented programming in Python, and I wanted a little rinky-dink program that said, I'm going to take a list, and I'm going to add 2 to that list. Well, we could look at it like this, right? So I could take my first line here. Did not like that. My computer's running really slow today, guys, so I apologize if it jumps around a little bit. So here is sort of on line 1 here, I've got this list. I'm going to call it my list, and I'm going to just sort of define it. 1, 2, 3, 4, 5. And the way that I would do this sort of object-oriented programming way to just sort of add 2 to every number in that list is I would just sort of change what that object was. Right? So here, because there's no built-in sort of behavior of lists to automatically add 2 to stuff, I sort of go through and I just say, all right, take every element in here, and then I want you to just add 2 to it. And then redefine this object, modify it, overwrite it. And sure enough, that gives me a case where my list is now a new representation of this. If this were a sort of truer functional programming language, it would sort of say, hey, you can't overwrite this data. You've already established it. And so there you go. Now, if I want to do a more functional programming approach, something I might want to do is I'd start off by sort of defining the function. So up here, lines 1 and 2, I have this, there we go. This new function I've made called add2, and add2 takes a value and it adds 2 to it. And I'll redefine my list down here. So here I've got this object, 1, 2, 3, 4, 5. And this is sort of the way functional programming is going to do things, right? What I'm going to say here is take my list and use this thing called map on it. We've seen map before in a couple different cases. This just says, take something that iterates things like my list, right, a list of numbers, and apply this function to each of those values. Map it out to each of these functions. And then I'm going to pass it into another function called list, right? And that's going to say, take the result of this map and just return it back as a list. And here I'm going to compare this to my original value of my list. And what's happened is that I haven't, scroll back a little bit, I haven't actually modified that underlying data. I've just passed it through a couple of sets of successive functions until what's come out is the value that I'm looking for. Right? And this is kind of, at a sort of like very broad level, what the difference between functional programming and object-oriented programming is. It's a little bit more nuanced to say than saying, oh, in one case we change objects and in the other case we don't. The idea here is really that I'm going to use some sort of object. I'm going to modify an object in place versus change how it's represented to me at the end. There's a lot of other stuff that's kind of going on behind the scenes. A lot of other stuff that we're skipping over. But this is the sort of core, in my mind, how I sort of look at a language and say, functional, object-oriented. Now, one of your questions might be, well, which is better? Or which works better? Or which is more appropriate in a certain situation? And the answer, the only answer I can give you is that there isn't a certain best value or best practice or best place for it to go. They're both good. They both add a lot of value to the world. They both do the same things. It's just sort of how you want to approach going through a programming problem. right? And they both have their own downsides. In Python, right, it's very easy to take something that you thought was a string and accidentally overwrite it so that it's a float or it's an integer or that sort of stuff. And so kind of keeping track of what the program state looks like and what certain variables are assigned to certain values is it can be tricky, right? And that's an object-oriented programming language problem. But within functional programming, we've got our own problems, right? We have to sort of constantly be thinking about, like, well, what does data look like? How's it being represented at each step in this process? What are my functions doing? Are they doing exactly what I think they should be doing? There's upsides and downsides to both approaches. This is just sort of to explore what these approaches even are to begin with. To tell you a short little anecdote, there's a language called Clojure, which I'll sort of like Google real quick, just so you can kind of see how absolutely insane this is. It's actually a really fascinating language. It's sort of built on what's known as the JVM, the Java virtual machine. So it takes care of all the virtualization and stuff that Java has, and Java is a very huge, nice language. But let's see if I can find something good here. Yeah, let's do functions. This is a good one. So here we go. Right over here on this side is sort of how Clojure looks like, right? And in this case, there we go. Here, I'm defining a function. So starting off with def, then the inputs. And you'll notice that each of these functions, right, is the first thing that comes into the case, right? So we're already oriented towards thinking, what is the first thing? What's the most primary thing? What's the thing that I care about? Functions. Here's a function called string. Here's a function called print line. Here's a new function I'm defining called say hello. If I were to do something like add two numbers together, it would look like this. +2, 2, as opposed to 2 + 2, right? Because what we're not doing is modifying that 2 to add 2 to it. We're taking the function sum and we're passing in arguments. So I tried for about 2 months on my sort of days off to get like really good at Clojure, and I couldn't do it. It is a very different dynamic and a very different paradigm that I'm used to as an object-oriented programmer, as a Python developer. But it's great, and I would, especially for those of you who have like some programming background already, when you've got the free time, right? Like after this course is over, go out, try to learn a different language. You'll learn more about Python than you will that language, and it's really fantastic. That's one of the best advice I can give you to become a good Python developer, is to do not Python for a while. Okay, so cool. I'm going to let some questions percolate up in this chat, and I'm going to take a second to drink my coffee. Oh, okay. Again, if you got any questions, like go ahead and throw them in the Slack. I've got it right over here. I can definitely answer them as they come through. So let's talk about classes in Python. So we've had this whole object-oriented versus functional debate. I'm going to switch back over to this GitHub for a second. And here we are. So we've kind of gotten this part, right? We can sort of, to a certain degree, define object-oriented programming. Michael in New York is asking, what new language would be the easiest transition from Python? That's a really good question. So that's a really interesting question, because a lot of the sort of same things that we do in Python, we're going to do in every language, right? Control flow, loops, for loops, if-else, assigning things, functions, taking the results of one thing and piping it into another thing. These are all things we do in every programming language. And if you can do them in Python, you can do them sort of anywhere. I would probably say like Scala would like probably be like a nice next choice. Scala, R, sort of depends on if you want to like keep doing data science stuff in a different language, or if you really want to try some like independent, not data science focused programming. So probably R. I mean, everybody, if you're a data scientist, you're going to learn R at some point. That's just, we all know enough R and enough Python to sort of make messes of things. Okay, well, let's jump into classes in Python. And classes are a type of object. And the best way I can sort of think about this, or I can help you think about this, is to consider it like this, right? A class sort of defines this blueprint. And every time we instantiate that class, every time we sort of create a new version of it or a new instance of it, it's going to sort of lay out the things that it can and can't do and sort of set it up in its default state. And a good sort of example is to imagine that I've got these two data frames, df1 and df2, and I instantiate two different decision tree classifiers, right, dt1 and dt2, and I fit them to two different sets of data. Now, dt1 and dt2, right, these two different decision tree classifiers are going to have the same underlying blueprint to this, right? Calling fit on both of them is going to do the same process of starting to fit that decision tree. Calling .score is going to call the same method for both of them. They're the same kind of object. They're going to do the same sorts of things. But they're each going to have different attributes, right? So because decision tree 1 sees a different set of data, it's going to create a different decision tree. It's going to create different splits, different nodes, different data. It's going to expect different columns. They can do the same things, but we're setting different values internally to them. And if I change one value on decision tree 1, it doesn't change the thing on decision tree 2. So when we instantiate this class, instantiate just sort of means to say, call decision tree classifier with a little like parentheses, we're creating a unique copy of that class. We're sort of copying over all the stuff internally that it can do, but we're letting it sort of exist in its own sort of memory space so that when we change values in there, like fitting decision trees, it stays there and it doesn't inform any of the other copies of that class. OK, so I've talked for 20 minutes, which is way more than I like talking as lead instructor. So let's sort of do a little check for understanding. We'll take a good 15 minutes for this. And this is going to be kind of a group activity. So go ahead and pair up or get into a group of no more than 4 and try to work through this example. So I want you to pick a pet, like an animal, a cat, a dog, a lizard, a fish, whatever you like. I'm sure some of you have really interesting pets. If you have a pet that is not a cat, a dog, or a lizard, or a fish, put it in the Slack. I'm really curious to see what other weird pets people have. And so together, sort of list out the things that every member of that pet can do, right? Like eat, shed, poop, that sort of stuff. Then sort of list out what the attributes of that pet might be, right? So different pets have different names, for example. And so we might have two rabbits. OK, apparently horses, rabbits. Oh, rock. Excellent. I like that. Let's go with the rabbit example, right? I might have two different rabbits. They both shake because they're really terrified, because rabbits are afraid of lots of things. They eat, they shed. But this rabbit's called Fluffy, and this rabbit's called Buffy. Buffy and Fluffy the rabbits. That works. Those names are attributes, right? They're unique to each instance of that rabbit. So think through what those attributes of those pets are, right? Things that might differ across the same pet. And then think through those, what we're going to call methods, right? Things that every member of that pet can do. Then I want you to sort of talk about things that those pets can do that other pets can also do, or that other animals could also do. So it's not just rabbits can eat and nothing else can eat. Rabbits can eat and cats and dogs. So that might be a thing that all pets can sort of share. So after all of that sort of like talking and discussing stuff, write down the things that all the animals can do, things that are members of your pet class can do, and then things that are unique to that specific pet. And this might seem a little silly, to sort of just talk about this stuff and write it out, but this is really good for helping you sort of break up how things have shared behavior or distinct behavior. All right, so I'm going to go ahead and throw a timer on there. We'll take 15 minutes. If your group finishes early, there's a little bit of an extra bonus section down here, which I'll let you all explore. So we'll come back in 15 minutes, and I might have one market come on and sort of just explain their findings. But we'll come back in 15. Okay, so I'm getting the message that we are a little ahead of schedule, which is great. So we're going to kind of cut that off a few minutes early. If you're still thinking through with your groups, that's awesome. Take the conversation to Slack. We're going to have Atlanta come on mic real quick and just sort of walk us through what they found for their pets, and we'll sort of kind of talk to that. So Atlanta, take it away.
Okay. All right. We have to go. Okay. We're going to kind of answer the 5 questions as a group of the 4 of us. So I'll take the first one. The pet that we selected was a spider, black widow spider, I think. Number 2, Frank, you're going to handle that.
Jesus. Spider. Basically, things that remember the pet can do. It can eat. It can lay eggs. It can bite. It can spin webs. It can molt. Thank you very much. It can crawl.
All right. Number 3, Caleb.
Oh, never mind. I'm doing number 3. What are attributes of a specific pet that might differ across each of the class, such as their name, how you got it, what you specifically feed it? Are there things that those pets can do that other pets can also do, other animals? Eat, move, reproduce, bite. That's a big one. What am I missing? Things that all, yeah, I think that's it.
That's what we got.
Cool. We'll move past 5. We don't need to yeah. So one thing I think is really interesting about that spider example, outside of the fact that now that I know that spiders could molt, I'm a little terrified of them. Is that there's something that is really super unique to spiders that other animals don't have, right? Which is this number of legs, right? So we might have most pets are going to have 4 legs. Spiders are going to have 8, right? So sort of thinking about what makes all of these pets unique versus what makes these specific pets unique, that can be really interesting. So we might have something where we say okay, what is the number of legs of my pet? We might want to say, yeah, most pets are going to have 4. Spiders are going to have 8 legs. So we're going to kind of see cases of this before, but sort of just keeping your mind open to what makes this distinct from other things that are similar to it, and then what makes things distinct from this that are distinct to this specific version of it. We'll kind of see what that looks like. But yeah, that's terrifying. That's more than I ever wanted to know about spiders. So cool. Let's actually go ahead and try some of this code for a bit. So we'll kind of work through here for the next 20 or 15 minutes. Then we have a sort of slightly larger check for understanding. And we'll do just the sort of thing where we'll take a break and also do the check for understanding, sort of do double work there. So let's talk about classes and inheritance, right? And if we go back to our sort of guideline for the day, we're going to talk about inheritance as well in here. So let's go ahead and pretend that we've got some sort of vehicle that we want to make, right? This is usually animals or vehicles are the way we learn classes, so we're kind of doing both. We might want to make this sort of generic vehicle class, right? This is going to be the thing that all vehicles do. And this is sort of the way that we define a class in Python. It's going to be these 2 lines right here. So we're going to start off with this class, CLASS. Notice that when we sort of define classes or use classes, we're going to use proper case to sort of denote that this is a class and not a function or something. So class vehicle, and all this thing is going to do is pass, right? We call it, it does nothing. There's a thing in here called object, right? And we'll talk about what that means in a second. This is going to relate to inheritance. This isn't like a function, right? So a function, whatever goes into that parentheses when we define it, it's something that function is going to expect to see next. Within a class, this acts a little differently. It looks the same, but it acts differently. So we'll sort of talk about what that means in a second. But this is a different thing than a function. And then what we'll do next is on line 4, we'll sort of instantiate that object, and then on line 5, we'll sort of evaluate it. We'll sort of make it run, right? So here, I'm going to create something called vehicle. It's going to be a specific instance of my generic vehicle class. Then I'm going to call off and see what it looks like. So I'll run that. And sure enough, here it is, right? Like this, this dunder or double underscore dunder main dot vehicle just says, hey, here's a vehicle object that exists within this sort of main function, the thing that I'm running for right now. This thing over here, this 0x114cdd, that's the memory address of where it's sort of stored. We're never going to need to know that. Python just kind of shows it for us anyway. So we're going to start off with this lowercase underscore or lowercase class. That's going to tell Python we're going to define a class here. We give it that name and then this thing called object. And this is what's known as inheritance. So inheritance basically says, here's a class that exists in one place. I want to copy that class and then modify it or change parts of it. And here I'm saying, because I've got nothing else I want to put into this object yet, I want to inherit from this thing called object. And what is object? Well, object is sort of the grandfather object of everything in Python. It's sort of, if you can imagine like the family tree, it's sort of like right up here at the top. Everything else inherits from object. It doesn't do a lot. It just sort of like kind of creates a few things that that Python is looking for. Object can't do a lot, but it's just sort of good like programming practice to make sure that your class inherits from it if it doesn't need anything else. So next up, let's give vehicle some attributes, right? These are going to be things that are unique to every instance or every version of vehicle that we create. And I'm going to create a number of wheels, a name for this car, the speed that it's currently moving, and a maximum speed for it. So let me scroll down here, and let's talk about this part here. Right, so line 1 up here at the top, class vehicle object, hasn't changed. It sort of stayed the same. The next thing that we have, though, is that classes are going to have different functions that exist inside of them, right? And I've tried to be very clear about like my language, but this is what's known as a method, right? It's a function that's internal to a certain class. So here we have a function, and this function exists within each version of that class, and that's what's known as a method. And this is sort of what defines the behavior of that object, right? This is what defines what it can and can't do. A list can sum up all of the objects inside of it. Inside that list object somewhere is a method, def sum, that does that. And let's sort of look through here, right? So this is a sort of special function. Come on. Sorry, there we go. Yeah, my computer is running real slow today. So I'll scroll back up to that cell. There we go. Come on, buddy. All right, well, there we go, perfect. Okay, so this is a special function. It's known as the init function or dunder init. So again, double underscore is dunder. And what this is going to do is this is going to be the function that runs whenever that object is immediately instantiated. So I say create a vehicle. It says, OK, cool, I'm going to create some stuff that exists within myself. So you'll notice that these functions start off by taking this object called, or this thing called self, right? This is a method. This is a function. It's going to require arguments, things that go into there. This self looks back and says, OK, whatever I'm going to use here is going to be distinct to whatever version of this vehicle I create. So every time I create a new vehicle, it's going to run that, and it's going to keep those things unique to that instance of it. And what sort of things is it going to keep unique to it? Well, it's going to keep a number of wheels. So self.number of wheels says, hey, this object, whenever it gets created, is going to have this thing, this attribute called number of wheels, and it's going to be equal to 4. It's going to have a name, which is equal to Kit. I think that's the Death Rider card, not Death Rider, Knight Rider, that's the one. It's going to have a current speed, and it's going to have a max speed. And these are going to be values that exist specifically for each version of that vehicle whenever we create it. This is just saying, hey, when you create a vehicle, here is the sort of setup I want you to do. So now in 9, right, line 9, we go ahead and we create a version of that vehicle. And then we say, OK, cool, now print all these things. Kevin in New York's got a really great question. Why do we call dunder init when we create new methods in a class? So we can create any number of methods in a class. We can call them whatever we want. That name, dunder double underscore init double underscore, is a special one. Python knows to look for that name and run that the second the one had started. So that's sort of why that's the case. It's sort of reserved. It's special. So cool, so let's run this. And what's gonna happen is I'm gonna define what this class looks like. I'm gonna run it, I'm gonna create a version of it called lowercase vehicle, and I'm gonna print out that object and all of these attributes. Notice none of these have parentheses, right? Number of wheels has no parentheses, name has no parentheses, current speed has no parentheses, all that sort of stuff. And that's because we haven't defined them as methods of this class. We've just said, here's a variable, I want you to keep track of it internal to that object. So I'll run this, and let's spin up. Okay, and here's my vehicle object. So that's the sort of output of just printing out vehicle over here on line 10. And then the number of wheels 4, the name kit, the current speed, and the max speed. And so we'll kind of like just do a little quick review of like breaking down what this looks like, right? So every class has got these internal functions. We're going to call them methods that, and when they exist inside that class, and they define what the object can do. We've got a special function known as dunderInit. This method runs as soon as a specific object to that a specific instance is created. We call that instantiation. When I do vehicle equals vehicle with parentheses, that's an instantiation of the vehicle class. So inside any sort of method we create for a class, that dunderInit function might detail things we want to be populated as soon as the object exists. Excuse me. And yeah, and it's going to kind of like run through every time it gets instantiated, it'll run everything that's inside of dunderInit. And then outside of it, we might want to go through and change that ourselves. Now we might want to say, hey, you know, it's all great and wonderful that we've sort of defined every vehicle that we exist to be called kit and have 4 wheels, but I might, as the user, want to change that. And what we can do is when we instantiate this class, we can let it up to the user to decide what that looks like by modifying what this init function looks like. So this is the part that's changed a little bit right here. And so here what I've done is I've said, OK, when the user creates this vehicle class, or when somebody creates this vehicle class and instantiates a version of it, they can also supply the current speed and optionally a name, right? And so here, that self is going to stay. When you're doing methods in a class, always put that self in first. But here, when I create it, I'm going to be able to say it, hey, here's the current speed of the vehicle I'm creating. And if I wanted to, I can change that name as well. So notice that down here, I've also changed lines 5 and 6. Self.name isn't kit anymore. It's whatever gets passed in from name. So name up here. Current speed does the same thing, right? We're going to set that internal attribute of that speed to whatever the user says it should look like. And if we scroll down a little bit, here, I'm going to create a vehicle. And now, instead of doing an empty parentheses, I'm going to actually fill it up, right? Because I know that the first thing that my vehicle needs is a current speed. How fast is it driving? And I'm going to fill that in. I'm going to put in 25. When I run line 9, Python's going to look at whatever this first thing is here, current speed, and it's going to go and drop it into that self.currentSpeed attribute, that sort of current speed that's sitting inside of that memory. It's also going to take the name Big Blue Van, and it's going to put it in for that name. And here is that again. So again, this line 11 through 15 is exactly what we did before. It's just sort of printing out the attributes of this vehicle. But when I run this, now I have Big Blue Van as the name, and I have 25 for that speed. So if you want your object to take in user input when you start, what you're going to modify is this dunderInit function to take in more things than just self, and then you're going to assign those values to self dot whatever you want to call it, right? I call the current speed and name and max speed. Depending on how you're making your class, it might do different things. But this is a way to sort of like create an instance of an object that the user has some input in on as well. If you were creating, say, a modeling class to find k nearest neighbors or something, you might want to have your user put in the number of neighbors you want, which is why when we instantiate k neighbors classifier, we say n_neighbors is equal to something, right? Same sort of concept. OK, Adjent, that's your question. I will pop into that in a second. So cool. if you use keyword arguments like we did up here, so for our keyword argument, right, current speed is an argument. It has to be there. If it's not in there, Python will yell at us. Name equals kit is a keyword argument. So we can optionally provide that, but if we don't provide it, we've sort of like supplied the default for our program anyway. So sort of just either one works out well. You just have to sort of think about like what your use case is. So let's scroll down here. Everything is going super slow. So yeah, so here's a little bit of code. If I had a car, I don't know why I chose vehicles. I hate driving. I'm really, really bad at it. So let's say this is my car, right? And I'm driving 10 miles an hour. It's the highway. People are beeping at me, but I'm super slow and super cautious. I might want to go through here and say, this, right? So I've kind of created this extra version of my car, right? So there's vehicle, which we did like in the cell above, and my car, which we did here. And notice that even though I didn't provide it a name, my car has sort of filled in that sort of default option of kit. But if I try now to create a vehicle and instantiate it without a speed at all, like here an error car is going to yell at me. And it's going to say type error. And we can kind of sort of walk through this sort of error message. And again, one of the best things I can tell you to do as developers is when you get these tracebacks, right, when things have gone wrong, really try to spend a couple minutes and read through it and try to figure out what it's trying to tell you. So here, it's saying dunder init is missing one required positional argument, current speed. Well, OK, I didn't feed anything in there. Let's take a look back at what the class looks like. OK, so it's looking for current speed. This is an argument. It's not a keyword argument. It doesn't have a default. I didn't pass that in there. Oh, OK, I see what I did wrong here. I needed to actually give a value when I did that. So so this works just the same sort of way as a function does. It's just going to sort of be internal to a class. OK, let me scroll down a little bit. Apologize for how slow my computer's running. So here we're going to change a couple things up, right? We're going to add in some extra methods. And when I say method, just think, OK, function that does stuff for a class. Hung is asking, how do you denote a required argument versus an optional argument? That is right here. So current speed is a required argument. It has no equal sign in sort of this line 3 where it gets defined. Name does have an equal sign right here. And so this is a keyword argument, right? It's optional. If I don't provide anything for name, it's going to fill it in with kit. All of your positional arguments, all of your required arguments have to come first, then all the ones with equal signs. So here, lines 1 through 7, we haven't changed at all. It's still the same sort of thing. Here, I'm going to set in a couple of new functions, right? New methods. And these are going to be things that I can call when I have an instantiated object. So let's look through a couple of these things, right? First, I'm going to have this thing called set current speed. Let me, there we go. So, oh, come on, buddy. OK, so cool. So here, lines 11 and 12, set current speed. And all this is going to do is when I call whatever I've instantiated this class as dot set current speed and give it a speed, it's going to look back at its internal version for current speed, and it's going to update it to what I set it to. So if I say set current speed to 60, it'll take that internal sort of stored memory of that speed and update it to 60. And then I'm going to put in this other one called check speed, right? Now here, because I've got no other arguments besides self, I don't have to pass anything into it. This is just me saying, hey, what is my current speed? And if it's greater than or equal to the max speed, right, here's my little if statement, I'm going to get this warning. Hey, you're going too fast. I'm going to slow you down. And I'm going to set, over here on line 18, this current speed to whatever that max speed is, right? Oh, no, I'm going too fast. Let me slow down. Otherwise, it's just going to tell me how fast I'm running. So I'm going to run the cell. I'm going to update what my definition for vehicle is. So here, right, I'm going to create this thing called death cab. It's probably going to something that's cute. And I'm going to give it a speed of 95. I'm going to give it a name called death cab. And then I'm going to do this new thing, check speed, right? So here's dot, check underscore speed. That's going to look into this class. It's going to look for a method called check speed, which is right here. And then it's going to run this method. All right, so let's scroll up. Come on, buddy. Come on, buddy. OK. So let me scroll up just a little bit more. Awesome, here we go. OK, so I'm going to run the cell. And so when I run the cell, line 1 is going to instantiate this version of vehicle where speed is set to 95 and cab and the name is set to death cab. And then it's going to run that internal method called check underscore speed. And it's going to say, hey, my current speed, 95, is faster than my max speed of 60. I'm driving too fast. Will, you are driving at 95. Warning, too fast, slowing you down. Gil out of New York is asking, how do I show the line numbers? Right over here on view. So you can change, do I want the header, do I want the toolbar, do I want line numbers? I like the line numbers because I can actually read those things. And here, I can hop down and I can say, OK, now I'm going to use that set current speed function. Remember, it had self, comma, speed. That 20 is going to get assigned to speed, and then it's going to get passed in and set as the current speed for my car. It doesn't return anything, it doesn't print anything, so I'm not going to see anything. And if I do check underscore speed again, hey, I'm driving at 20 kilometers, 20 miles. We're going to sort of not worry about regionalization. Thank you for driving safely. If I wanted to come through here and I wanted to just manually set these attributes, I can. I can duck in there and change these things. So here, deathcab.number of wheels, I can just go through and say, take whatever value's there and replace it with 3. And now all of a sudden, there it is. But we might have different vehicles, right? Like certain vehicles have different numbers of wheels, right? And I might want to create a class that's called bicycles. And bicycles default to having 2 wheels. I might want to create a truck called 18-wheeler trucks, and that's a lot of coding. How would I kind of have this behavior shared without having to go through and find and copy this code a bunch? And this is a good sort of warning for you as newer developers. If you find yourself copying and pasting former code to somewhere else, that's a good sign that you probably want to either create a function or a class that does that. You don't have to do it all the time, but if you create 2 versions of code that sit in 2 different places and you need to change both of them, that's a lot more work than having it in one place and just changing it once. So for me, my mental record is if I got to copy and paste it 3 times into 3 different places, that's when I stop, I refactor, I create a function, I create a class. And that way I don't have to kind of remember where everything is. So let's talk about inheritance, right? And we'll kind of spend another 10 minutes on this, and then we'll sort of take a longer break and some time for checks for understanding. And this is going to kind of, I'm hopping back to the GitHub for a second. This is our 3rd section, right? Inheritance. And we've already sort of talked about self, so we're really kind of we're kind of going down the pipeline pretty fast. So here, I'm going to create this class called bicycle, and it's going to inherit not from object, but from that vehicle class that we made before. And what I'm going to do here is sort of a little bit of like Python magic. So I'm going to create this init function, just like I did before, and it's going to take in a current speed, it's going to take in a name. What I'm going to do here is I'm going to call this thing called super, super parentheses open close. This is sort of like a little magic Python-like thing that says, hey, you've inherited from an object, go up to that object and run that version of this method, right? So when I run this line, when I run line 4 over here, it's going to go and it's going to run the version of init, of dunder init, that exists in vehicle, not the one that exists here. Then in lines 5 and 6, I'm going to go through and modify those things. So vehicles init function says, set the number of wheels equal to 4 and the max speed 60. I don't know about you, I can't ride my bike faster than 10 miles an hour, much less 60. Also, my bike has 2 wheels. So we instantiate this object, it sets all these things, and then we come down here in line 5 and 6 and reset them to what we want, which is bicycles start off with the default number of 2, and they have a max speed of 15 miles an hour. We're also going to add in a specific method that exists here for bicycles that doesn't exist for other vehicles. In this case, it's going to be called ring bell. And when we call ring bell, it's going to print out bring to our screen. So I'm going to go ahead and run it. Let me check. Yep, so I have run that cell. When we inherit from this class, we can go through and we can either override a method that exists already, like we did with dunder init, or we can add new functions, like we did with ring bell. And super is going to go back and say, like, hey, look at the class I'm inheriting from and run that version first, or run that method of it. In Python 3, super already kind of passes in self, so we don't have to worry about it. It's going to run it and then apply those things to our instance of bicycle. If we were in Python 2, there's other sorts of like nonsense that we have to do. So this is sort of one of those cases where Python 3 is almost always going to be better, but here is much better. So let's go ahead and see what this looks like in person. I'm going to set up an object called car. My car is stopped. It's at 0 speed. I'm going to set up an object called bicycle. It's a bicycle class. It's starting at 10 speeds. So I'll run that cell. And now they've sort of existed, right? I've got a car object sitting somewhere, and I've got a bicycle object sitting somewhere. And I'll check the speed of that car. The car is driving at 0, so it's not going anywhere, and that's very safe. There is no safer speed than not moving at all. And our bicycle is driving at 10. That's also safe for a bicycle. And we can go ahead and sort of look at the number of wheels. It's been set to 2 because of this line right up here on line 5, right? We sort of set up everything that the bicycle has, and then we've reset that number of wheels to be 2 as opposed to 4. Now, if I run the ring bell method here, bicycle's going to say, bring, I've got a bell. I'm going to ring it. It's cute. I'm maybe going to listen to Queen after this and listen to Bicycle. It's a good song. But if I try to run this for car, it's going to error out on me. And that's because the vehicle object doesn't have ring bell. The bicycle object does. So it's sort of taking everything that vehicle has, right? In our bicycle object, we never defined check speed, right? I can look right back up in my bicycle code, and there's nothing in here that says I have a method called check speed, right? I've got 2 methods. I've got dunder init, and I've got ring bell. Inheriting from vehicle here has pulled those other methods down and made them part of it. So I can call everything that vehicle has plus this new stuff that's inside of bicycle. So the amount of new code I have to write is actually much smaller. It's very good. As developers, it should be your goal to write as little code as possible. You should be extra, super lazy. I tell people this all the time. Be really lazy. It's very easy as a developer to over-engineer things and do a lot of work because it's cool and it's fun and it runs. No, do as little work as possible. Work smart, don't work hard. So okay, so scrolling down very slowly because my computer has decided that it is the slowest thing in the world. Let's go ahead. What we'll do here is we'll sort of take 20 minutes. We'll sort of bundle this into your break as well as sort of this check for understanding. This is a pretty extensive check for understanding, so don't worry if you don't finish it, but do try it, right? This is a chance to kind of like really dig into the guts of Python, to poke at things and see what they do and work. The best sort of mental framework for this is before you run it, say, I think I want to do X. I think it's going to do X for these reasons. Run it and see if it confirms or disconfirms what you're thinking. That's the best advice I can give you. So I'm not going to run too quickly through it, but there's kind of we're going to modify that vehicle class to do a different couple of things. We're going to change the attributes. We're going to change, we're going to add currently writing. We're going to add these 3 different methods. So add a passenger, let a passenger off, and talk about the current passengers. Step 2 is going to sort of force you to say, if my code is working, this should be the output. Let me see if it gives me the output that I want it to give me, right? This is sort of a sort of ersatz like fake sort of testing thing. I do this with my code all the time. I think it should do X. Let me run this sort of test case to see if it does X. Aha, it did X. That's probably working. Or no, it did not do X. I need to go back and take a look at it. And this is sort of going to ask you to sort of do something like that, right? And it can be as simple as writing a comment that says, if I call number of wheels, it should give me back the number of wheels, and that should be 4 in this case. Let me do it. Hey, it was successful. And then, kind of modify the bicycle class, create a new train class, sort of spend some time like pushing at this stuff to try to work this out. There's sample code, there's solution code in the other notebook. Don't worry too much about finishing it, but take this opportunity to really try to challenge yourself to push on Python. Also take this opportunity to get coffee and stretch your legs and walk around. So we'll take 20 minutes for that. And I will see you all back at 10:25 Central, 11:25 Eastern. If you have questions, ask your local instructors, put them up in the Slack. We can definitely start some threads and kind of talk about things that are working or not working, but enjoy it. It's really fun to sort of work through these things. And I will see you all in 20. All right, let's keep moving forward. So hopefully that exercise with classes was helpful. I don't really expect everybody to get through all the way through it because it's a pretty large and extensive check for understanding. One really good way to sort of practice classes is to maybe during the lab or afterwards, go back, try to do it again without looking at the solutions and see how far you get. The solution codes can be a really, really good help, but make sure that you're also trying out that coding as well, as opposed to just looking at the solution code and taking that for understanding. So cool. So the next thing I sort of want to do, right? I'm gonna switch back to the GitHub and sort of look at our sort of goals here today. And our goals, are to look at through object-oriented programming, to talk about what classes are, what inheritance is, what self is. We've kind of mostly, for the most part, gotten through that. What I want to talk about now is why we might do these things. And the reason, and the way I'm going to sort of talk about this is I'm going to help us build out sort of an extension library to scikit-learn using the things that exist in scikit-learn already. And the reason I'm going to do this is that that's going to feed very closely, very well into our discussion about data pipelines, which sort of rely on these sort of class things. The two sorts of ways that you end up using classes is that you're going to start either making your own from scratch to do the things that you needed to do, or you're going to take the stuff that already exists in the library and either modify it or add some new functionality. And here we're going to take that second case, right? This is going to be replicating the work that I've done to kind of create a class that I really like in scikit-learn that doesn't exist yet. So let's go ahead, right? And we're going to kind of like walk through. This is going to be like half sort of talking about like what the guts of scikit-learn looks like, and have sort of us applying this here. There's no check for understanding here. This is more just to kind of take us through a use case of how these skills might be put into play. And we're going to apply this by creating something called a feature extractor class for scikit-learn. And what we're going to do here is we're going to create a scikit-learn object. It's going to have a fit, and it's going to have a transform method that we've seen before. And what's going to happen is if we give it a pandas data frame and a column, it's going to extract that column and give it to us as a NumPy series or as a NumPy array. And why would we want to do this? Well, we're going to see this when we sort of talk about data pipelines and the pipeline object in the last third of the class. This is going to be a really, really helpful thing. More importantly, like this is going to be a great way to sort of take a look at what's happening under the guts of scikit-learn. So this portion here, right, before we sort of get started, it's taking advantage of the fact that I've worked with scikit-learn for 5 or 6 years now, and so I know where things are and I know what to look for. We're not expecting you at this point to be able to have the knowledge of scikit-learn or the experience with Python to just drop down into the documentation and find it, right? This is an example of what we're seeing of sort of what a more intermediate or advanced developer would look for, to sort of give you that start to say like, okay, in the future, when I've leveled up my skills and I know what I'm doing, this is the kind of like use case that I might use this for. So don't worry, about me saying, oh, of course it's over here. That's experience talking. That's stuff that you'll develop as developers moving forward. But we're going to make use of this thing called a mixing class. So what's happened here, right, is scikit-learn has a bunch of different libraries all working at once. And there's a lot of shared behavior that each of those objects has. So all of our pre-processing libraries does stuff like fit and transform. All of our modeling libraries do things like fit and predict and that sort of stuff. And different types of models might also have shared behavior, right? Every regression model is going to like sort of rely on R². Every classification model is going to rely on accuracy. A mixing class is sort of a default empty class that has those certain behaviors sort of coded up, right? Because different modules of a certain library are going to look to work together, and they're going to expect that they have those things. And within sklearn, these mixing classes are kept in the space library. And I'm going to sort of jump back and forth between that notebook and that documentation. And so here we go, sklearn.base, and there's a whole bunch of different mixins here. So base estimator, classifier, regressor, transformer mixin, these are all just sort of like base classes that we're then going to inherit from and modify for our own uses. And within scikit-learn, these also get modified. So for example, here's logistic regression, right? We've done logistic regression before. And when I switch into this, it's not going to take us to the documentation. It's going to take us to the actual source code that you run, that your computer runs when you run logistic regression. And so this is the great part about open source libraries, is that we can just actually walk right into there and look at what other people have done. So here, I'm going to zoom in a little bit so we can actually read this, right? Here's the line that we're looking at. This is line 962 of scikit-learn.linearmodel.logistic.py. And look, it's a class. It's a class called logistic regression, and it inherits from base estimator, linear classifier mixin, and sparse coef mixin. What are all of those things? Don't worry about it yet. You would have to be a developer on scikit-learn to really know what each of these things do. But it's sort of taking in those same things that we've just talked about for the last hour, and it's making use of them for our purposes, right? And those three things, base estimator, linear classifier mixin, and sparse coef mixin, provide different standardized methods and structures so that logistic regression works just the same way as everything else does. Standard scalar does the same thing. We won't go and look at it, but you can click on that on your own time and go and poke around in the source code. So what this means is that all of our pre-processing libraries in scikit-learn, and to an extent our modeling libraries as well, pull in different things from base estimator and transformer mixin. And that gives us these three methods that are already defined. Get params and set params, which we don't have to really worry about. That's just internal scikit stuff. And fit and underscore transform. And what scikit-learn is looking for is if we create a new class in scikit-learn using these things, it's going to expect that we define .fit and .transform, and it'll handle everything that happens with fit transform. So why both fit and transform? Well, in this case, right, our class doesn't need to remember anything. It doesn't need to sort of like keep its own internal gears working, right? It's just going to look at like some sort of column and just do it. But things in scikit-learn expect to see .fit. So we're going to go ahead and create one for it just so that things kind of work well with it. And these are the sorts of use cases, the sorts of things you have to keep in mind when you're modifying or sort of extending other people's codes. Is what are they kept in mind? What are the things that they expect to see? Good. Let me put that in there as well so that everything works really nicely together. So first thing I'm going to do is I'm just going to create some fake data for testing, right? Here's a little data frame. I really like this from_dict method. This lets you pass in a dictionary where each key is the name of a column, and each value for that key is sort of the set of data. I really like you doing this sort of stuff. For me, it makes sense, but you can sort of create a data frame however you want. But this is just going to sort of create a data frame that has 5 rows. Column A with 1, 2, 3, 4, 5, and column B with 6, 7, 8, 9, 10. Don't worry too much about that section. That's just to sort of set up this test data. And here we'll sort of set up the basic framework for our feature extractor class, right? And this is just going to take in a pandas data frame and a column name and get rid of everything but that column. And I'm just going to go ahead. I'm going to grab class. I'm going to go through and say like, OK, inherit from base estimator and transformer mixin. And here are my two methods, right? Fit. And what I've just said is like, whenever it gets called, I want to print out called the fit method. And transform. Whenever it gets called, I want to say print called the transform method. Now, because we've imported, because we've inherited from base estimator and transformer mixin, there's a lot of other stuff that's sort of been brought into feature extractor. But there's also stuff that we've defined ourselves here. So if I instantiate it under FE and then call fe.fit, it's going to print out that statement, and it's going to print out the line called the fit method. And if I do .transform, the same thing's going to happen as well, right? It's going to look back into itself. It's going to say, OK, when I call .transform, I print out this line, and I pass. I do nothing else. So because we have inherited some of these other things, we have access to fit_transform as well, which we know is going to do a fit and then immediately transform the results. But when I run this, I'm going to get a big old error. And here it is, right? Fit transform is missing one required positional argument x. We've seen this error before. This is saying that this method, fit transform, needs something called x, and we didn't provide it. And so everything kind of collapsed. And so this is because we need some sort of x variable. And this is sort of standard templating across all of scikit-learn. A lot of the classes are looking for either something stored in a variable called capital X or stored in a variable called lowercase y, referring to the features and the target. So let's go ahead and pass in our data frame, right? If it wants an x, we'll give it an x. And if I run this, oh, now I've got a different error, right? And here, fit takes one positional argument and two are given. So what it's trying to do is it's trying to pass that x into our own fit method. Our fit method doesn't take in an x, and so it blows up, right? So fit_transform, which we've inherited from another library, wants an x. Our version of fit doesn't want an x, and so there's sort of a crash here. We're going to fix this in a second. Do the other methods from base estimator work? They do, right? Get_params, which we haven't defined, works just fine, right? What are the parameters of my class? Nothing. So there's also the set parameters. Again, we don't have to really worry too much about what these things do. They're just sort of internal Python things or internal scikit-learn things, but they do run successfully, which is good. So now we're going to go through and we're going to sort of change that feature extractor class that we made to do different things. And what I've done here in this section is whenever I've modified a line, I'm kind of put this comment under #newline next to it, so you can kind of see where things have changed. And all I've done here is I've modified fit and transform to take in an x. So when we call fit_transform, it'll take what we feed it, it'll pass that into fit, fit will be able to take it, it'll pass it into transform, it'll be able to take that as well. So this is just sort of to kind of bring our class in line with what scikit-learn wants. So we run it, and let's test it. Up, that's an error. What is happening here now? Okay, none type object has no attribute transform. That's a different error. If you run this and you get a different error than the one you got before, that's a really good thing. That means that you've made a change that's actually had an effect. I am always super excited when I can't figure something out, but when I change something, I change the error message. That's actually a really good sign. There's also one really, really good thing here, which is we know fit got called because it printed it out to screen. It said, I called the fit method. It happened. So something happened with what came out of fit and went into transform. And to sort of debug this, I've kind of copied over some code from the transformer mixin Mama library. And what this does is it says, hey, I take in an x, I take in a y. Don't worry about the star stuff right there. That's extra keyword arguments. Here's the line that's doing this stuff. Take self, so take whatever object I've got, call.fit with x, y, and fit params on it, then call.transform on x. So it's passing things through, right? Take x, pass it into fit, take whatever comes out of fit, and pass it into transform. Well, what comes out of fit? Nothing is coming out of fit right now, right? We're passing out nothing. We're just passing. We print out something, and we pass none. And what we've done is we've returned none back to transform, and transform goes, I don't know what to do with this. So what we'll do here is if we want to do stuff and then return back our own object again, and this is just sort of a thing that that scikit-learn is expecting, we're going to do return self. And that's just going to say whatever comes out of this method is going to be the same class again. This is sort of like a pretty advanced, higher level part of scikit-learn. If this doesn't immediately make sense, don't worry about it. This is just sort of behavior that scikit-learn is expecting. Not every library is going to have this. Every library is coded by different developers. It does different purposes. But we may want to sort of chain different methods together within a class, and this will let us do that. If you take a peek here, right, you can imagine self calling .fit, and then we want to call .transform on self again. And returning self helps us sort of pass it from here to here to here. So let's change what that looks like. Oop, I've gone a little too far. And so here, right, now I've changed this line over here on fit to return back our own object to ourselves. We can kind of see what's going on there as well. And now I need to reinstantiate a feature extractor, and I'm going to call fit transform. And when I do this, hey, It did it. It called fit, which does nothing but print something out. It called transform, which does nothing but print something out. That's awesome. So now all we have to do is go back and change fit and transform so that it does what we want it to do. And this is sort of the way that I'll try to like address sort of building out a class or building out something like this, is to go through and just say, all right, let me just have it print to screen whenever I want it to do a certain step. If you can get it to print something, you can get it to do what you want it to do. So let's take a step back. Let's look through this sort of thing. What we want our feature extractor class to do is when we instantiate it, we want to be able to give it a column name to look for. If I want to look for column B, I want to pass B into that feature extractor class. When I call .fit, I don't want it to do anything. When I call .transform, I want it to give us back a NumPy array with the column that matches the name of that column that I've given it. Why not a data frame? Different stuff in scikit-learn just works better with NumPy. NumPy is like the sort of underlying library across both of them, so we're just going to drop it down to that level that helps out there. Step 2, making .fit do nothing. We've got that finished. It's good. Don't need to change anything. So let's change step 1 first. And so that we want to have, when we instantiate it, we want to give it the name of a column. So let's do this. We'll add in this dunder init function, which we've seen before, right? Just these 3 lines. Def dunder init, I take in myself, and I take in the name of a column. I'm going to have it print out to screen to say that I've done it. And I'm going to set in this sort of internal variable, self.column equals column. So I give my feature extractor class a column. It's going to hold on to that and wait. So everything else here is the same. I'll go ahead and run the cell. Cool. So line 14, I've sort of instantiated. I put it in this object called FE. I've given it the name of the column B. I fit transform df. So when line 14 runs, it calls initialize class. When line 15 runs, it called the fit transform method. I can print out that attribute. So .column, which I've given it, it'll print it out. It's called B. And now getParams and setParams have now they have things inside of them, right? And this is sort of the way that Python or that scikit-learn holds track of different hyperparameters or different options that you set across the way, literally as a dictionary or some sort of object that's like got a setting. So now, because I've set in this new little attribute called column, it exists now in my object, and I can call other scikit-learn methods to do things with it. We're never going to directly, as end users, really use these things, but they're really helpful for scikit-learn to do their work. So cool. Now we're going to change the transform method, right? I instantiate the class, and it pops up. I give it a column name. That part's good. Fit doesn't do anything, which is perfect. That's all we want it to do. And now we're going to change this transform method. And I'm going to change a little bit of the boilerplate code here, just so that if we do get a y, we can ignore it. So our new line over here is, now fit takes in an x and a y equals none. So if I get a y, just if I don't get a y, don't worry about it. And down here, right, now transform calls the transform method and returns back the data frame with that column that we've established over here, .values. And so let's go ahead and run this cell. And awesome, right? So now we don't see anything new. That should have transformed our data, but it hasn't actually done anything. And that's because if we look at line 15, we're sort of creating this and then immediately throwing it away and printing out other stuff. So we'll change this one more time just to print out the results of fit transform. And that's going to look like right here. I'm just going to change it so it prints out the result of fitting and transforming on our data frame. And now we have a scikit-learn object that I give it a data frame. So that code is all in your notebook. I've not added a new thing at all. But now we have code that will actually we give it a data frame and a column name. It gives us that value. All the code for this is straight in that notebook. I haven't added or changed the thing yet. And so now I'm just going to go through here. This is sort of the final version down here. I just removed all those print statements because we don't need to see them anymore. Okay, cool. So this is sort of like a, we're not expecting you to go through and modify scikit-learn libraries out of the bat. I'd coded for about 2 or 3 years before I even started going through that. This is more to say like, here's a discussion about classes. This is how it might be used by you in the future. So sort of keeping in mind, this is the way that these libraries are written, that they rely on these things, that there are these sort of like dynamics and these paradigms at play. Don't worry about replicating this or doing it yourself. This is just to say these exist. So, because I kind of want to do pipeline in one big stretch, let's go ahead and take let's take 10 minutes for a break. Go ahead and get up, get coffee, stretch your legs. We will come back in 10 minutes. That'll be 10:55 Central, 11:55 Eastern, and I will see you all then. Okay, cool. Let's get started. We've got about an hour and 5 minutes left, and we're going to sort of talk about these last couple of bits. We're going to talk about data pipelines and why they're useful, and then we're going to talk about the pipeline object and the feature union object in scikit-learn to help create a data pipeline. These are two of my most favorite classes in scikit-learn. It is amazing. When you can really sort of, it forces you to really think strongly and competently about like all the mechanics that are happening behind the scenes at a code level within scikit-learn. But if you can implement them well, it is such a boon to sort of productionalization and putting your models out there for people to use. It's really, really exciting. So I'm very, very excited to be able to share this with you. Okay, so let's talk about data pipelines, right? If you remember from a couple weeks ago, we talked about this typical data science workflow, right? So we get some raw data, we split it out into training and testing sets, and then we do all of this work, and we kind of create some transformers to transform the data from its raw state into what we're looking for, and then we create a model and we fit it. And we apply those same transformations to the holdout data, and we test it against that test set. And then we do it again with new data coming in. We've got transformations and a model. And what you can really do is you can imagine this being like a whole pipeline, right? In comes raw data, apply all of these transformations to it, pass those into this model, get out predictions at the end. For those of you who play video games, I've been playing this new Super Mario game that came out recently, and all it is pipelines, right? Mario goes in one way, he does some stuff, he comes out the other end with maybe a new ability or a new hat or a new like power moon or something. So this whole thing right here, right, apply the same transformations to a certain set of raw data, then spit out predictions at the end, is something we're doing in 3 different places at the very least, right? We're doing it here when we train it, we're doing it here when we test against our holdout set, and then whenever new data comes in, we're doing the same thing. So a pipeline really is saying, OK, what are the steps I need to do to go from raw data to predictions? Yeah, there you go, Odyssey, yep. What are the things I need to do from my raw data step to my actual, I've got predictions in hand step? Let me codify that into one sort of step, one sort of set of things to do. And let me just reproducibly do it over and over and over again. So you can kind of imagine, like, if we take a little step closer and go, like, how might this look like in scikit-learn? We fit all the transformations to the training data. We transform that training data. We fit the model to that transformed training data, and we predict it, right? And then if we did this a bunch of times and we said we were pretty happy with it, OK, now let's transform this incoming data and predict. So when we fit, we're going to kind of be doing fit, transform, fit, transform, fit, transform, fit, transform. When we deploy this model, right, and it's just kind of sitting there ready for new data to come in, it's going to go transform, 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 transform. So what pipeline does, and so now I'm going to kind of go from like what scikit-learn pipeline, what data science pipelines in general look like, right? Which is just saying, here are all the steps I need to do to go from raw data to finished predictions. Scikit-learn has a library called pipeline that sort of lets you chain together different scikit-learn things so that you can sort of fit them all in one step and transform them all in one step versus going raw data, fit binarizer, transform binarizer, take that binarized data, decision tree classifier, fit it, transform it, predict it. Pipeline lets you chain these things together. And it is really fascinating. Now, the way to sort of think about this, I'm going to switch over to my whiteboard real quick, because this is just going to be easier to sort of show off with via sort of this via sort of like just a drawn out picture for a second. You can imagine one of two things happening, right? We have this. We have some steps that we want to take in serial, right? So we want to kind of go through and say, like, OK, I want to get my data. I want to take out this column, so we'll call it column B. I want to transform this so that it creates a bunch of dummy columns. So B1, B2, B3, B4. And then I want to put this into a model, right? These are all sort of serial steps. They happen one after another. So We take that data, we extract it, we do other things to it, we fill in the nulls, and we put it somewhere. So these are serial steps. We also might have parallel steps. So here's the thing where maybe we have things that I might want to do to column A, and things that I might want to do to column B, and things that I might want to do to column C, right? And they're all going to have one sort of mother step, right? So get data. And then we're going to do all of these steps at the same time and sort of join those results back together. If you can think through your data science pipeline into what steps can happen one after another and what steps should happen all at the same time and be joined back down together, then you are in great shape to apply the scikit-learn pipeline, right? And what this will typically look like is a series of steps that are joined together. So we might have one get data step. We might have a whole bunch of transformations that are happening in parallel, right? So this column requires some sort of thing. This column requires a different set of transformations. This one, this one, this one. We'll join them back up together once they're all completed. Then in a serial process, right, we'll pass that into a model. And then we'll get predictions. Woo! And that's literally what we're trying to do here. And it's going to be this combination of serial steps and parallel steps. And the pipeline object sort of lets us do both of these things at once. And as long as you sort of think through what needs to happen at the same time and get joined back together, and what needs to happen after something else is finished, you'll be in good shape. We'll sort of like walk through what this looks like in general, but I kind of want just to put that out there to get you starting thinking about these things. So serial steps, right? This is going to be the pipeline class. A pipeline object in scikit-learn lets you set up a series of steps that exists. No, go away, iTunes. You are terrible. It lets you take up a set of steps and it lets you sequentially feed data through those steps. At every step in that pipeline, it's going to call fit, and then it's going to call transform and pass that result down to the next one. At the very last step, it's going to fit it and then do what you want at the end of it. So if you wanted to call .predict on something, you would do pipeline.predict. And this pipeline object is going to look for a list of steps. And it's going to be a tuple with the name of the step and then the step to take. And these can either be already instantiated or they can just be passed in directly without being instantiated. We'll sort of take a look at what that looks like in a second. So what we'll do here is we'll sort of, like just to sort of test this out, we'll grab the iris data. We're going to use that feature extractor class that we made before, because there's a reason why I built it, to go and grab one column out of it. Then we're going to use binarizer from the preprocessing library to transform that column to have a cutoff. And then we're going to feed that into K-neighbors classifier. So this first part is going to be just sort of like doing train test and split to get this going. So this is just some sort of splash code. I'm going to import iris. I'm going to turn the species into zeros, ones, and twos. I'm going to apply it, and I'm just going to look at what that looks like. So Kelvin asks, are pipelines model independent, language-based in this case? Other languages may offer the same or similar features. They may offer some similar features. This is like a really scikit-learn way of doing things. Different languages are going to do things differently, or you may have to just sort of put it together yourself. There's quite a few options. Anyway, that whole like sort of boilerplate up there is just to get iris data into our set in memory, ready for us to go. And what we'll do here is we'll grab species, we'll put it off into its own variable, and we'll use train, test, and split, and sort of create the same training and test set for all of us, right? Here we have a random state. We'll all have this random state set, so we'll all have the same sort of version of data together. And so I'll run this, and now I have a X train and a Y train and an X test and a Y test. We've all sort of done this before a bunch of times. This is just to kind of keep things moving. OK, so next we're going to set up these steps that we want to do, right? We want these steps to happen in a sequential order. We want to take petal length. We want to pull it out of the data set. We want to turn it into a dummy variable with some sort of cutoff. Then we want to predict the flower species using just that one feature. And we're going to list out these steps that it looks like this. some sort of string which has the name of the step that we're calling it. We define this. We decide what it looks like. It can be, feature extractor step. It could be FE, like whatever you want to name it, and something that is a callable. This is going to be a class that has a fit and a transform method. The last item in this list of steps, instead of having .transform, can have .score, can have .predict, can have .predict prava, but everything in the middle is going to have transform. And this is what that's going to look like, right? Here's the modeling steps. It's a list. So we've got these brackets, each of these is a list. Line 2 is the first element in this list, and it's going to be a tuple with parentheses. First element being the name of the step, which we've defined. I'm calling it extract petal length. And the second part, so the second element in this tuple, is going to be grab feature extractor, looking for the column petal length. Then we're going to do binarizer, and the value for that is going to be whatever the median petal length is. And then we're going to predict using KNN. So extract the column, bin it, pass that into K-neighbors classifier. Right now we haven't set up it. Right now this is just a list of things. But if I run this cell, we can sort of see that it's a list of tuples, name a step that we're going to do. So then what we'll do is we'll go ahead and we'll instantiate this pipeline object. Again, all of my imports are up at the very top of the notebook, so I can just kind of call this here. And I'm going to set it to this object called model1. And I'm going to pass into this class that list of steps, where each step is a tuple with a string and then the actual scikit-learn object that we want to do. So I'll run this. It's just going to pop out and say, like, hey, I'm a pipeline. Here are my steps. Do feature extractor, do binarizer, do K-neighbors. And then I'm going to call .fit. And what this is going to do is it's going to go all the way up to the top step. It's going to fit. It's going to transform it. It's going to go to the next step for binarizer. It's going to fit it, and it's going to transform it. And then it's going to go down to the last step, and it's going to fit that K-neighbors classifier on the data that's been passed down, and it's going to get it ready for predictions. So let's run this. And so now model 1 acts like a K-neighbors classifier plus all of the transformations that classifier needs to work. So instead of having to say, let me make sure all of my data is right and ready to go, and then pass it into my fit model object, now I can just say, here's my raw data. I fit my pipeline. When I pass in my raw data, it's going to go through and change everything for me without me having to worry about it. So now I can just do everything else that K-neighbors classifier expects, right? Here's model1.score on X train and Y train. Now, I haven't touched X train or Y train yet, right? All I've done is pass it into that pipeline, but it's gone through, it takes it, it grabs out that petal length, it bins it, and it puts it into that fit model, which is pretty phenomenal. Here's where it's really cool, though. Here's X test and Y test, which I haven't touched yet. Look, I don't have to worry about transforming my test set and my training set and remembering which transformation happened where, and did I change my test set to look like my training set? No, the steps are set. And so I can pass in any data frame that has that petal length column, and it'll do the same transformations to it now that it's been fit. It's so cool. I can call .predict on it and get my predictions as well. OK, so cool. So I hope you all are as psyched as I am, because I'm really psyched. I love pipelines. They're really fun. We're going to do a couple of checks for understanding throughout this part. We're going to do, this is going to use a data set from the University of California, Irvine's machine learning repository on abalones, which are a type of snail. And apparently, it's a very difficult process to figure out how old an abalone is, because you have to cut the shell open and count rings using a microscope. So researchers wanted a model that would like estimate the age that they are. It's got these different features: sex, length, diameter, height, a whole bunch of weights, and rings, which is the age. So here I've just kind of done a little bit of like sort of default work to get this ready to go. Basically, just grabbing it from the internet and downloading it. Looks kind of like this. You'll be able to do that on your side as well. Our data set looks like this. So we have 4,177 entries up here. And it looks like we have no missing values because all of our stuff is 4,177 non-null values. And we can do this, we can model this in a couple of different ways, right? We could say, let's use our age, our rings value as a continuous variable and try to use a regression technique. We could try to predict each individual number of rings as if it was its own class. Or we could create a new feature and try to just predict a dummy variable. And we're going to do that third option. We're going to try to predict whether or not an abalone is above the average age in our sample. And this sort of code here, this is just a bunch of setup code, just says, OK, cool. Grab rings, and I want to just kind of set it above that average. And it's going to look like this. So we've got 4,177 values. Our age is, this is our dummy variable over here, right? 49% are below average, 50% are above. Pretty simple. That's going to be the thing that we predict. So our target column is now stored in Y. Our features are now stored in X. Use this abalone data set. We'll take, how long is this one? We'll take 10 minutes. Use train, test, and split with a test size of 0.25 in this random state to create train and test samples. Feature extractor, polynomial features, standard scalar, and logistic regression have all been imported already. So make a pipeline that takes out the diameter column using feature extractor, creates polynomial features for that term squared, that term cubed, standardizes them, and feeds them into logistic regression. Create a pipeline, fit it using X-train and Y-train. Without refitting it, use it to score X-test and Y-test. And if you have time, try to grab the predictions and use confusion matrix and classification report. We'll aim for 10 minutes. If we need more time, we'll take more time. So go ahead and have at it. If you have questions, please put them in the Slack, and we'll sort of work through them. Otherwise, we'll check back in 10 minutes. All right, cool. So hopefully you got some work through on that. Again, all these checks for understanding do have solution code in that solutions notebook. If you didn't get all the way through, that's fine. It's absolutely great. On your own time, try and reproduce it, and then use those solutions to help guide you towards that full answer. So cool. I'm going to go through here and just sort of paste in this code real quick, which I will Slack out. It is just the code that sort of splits it into training and test sets for us. So this is sort of pretty helpful. It's the same thing as is in that solution code, but it's not here in the notebook, so I just want to go ahead and put that in here. So I do have access to xtrain and xtest. Now you might be thinking it's really a lot of time to go through and name all these steps and then move forward, and then name all these steps and move forward. And the coders and developers of scikit-learn would agree with you, which is why they have made this helpful function make pipeline, where instead of creating a list of tuples with names and that sort of stuff, we can actually just go through here and just feed in comma by comma each of these steps into the make pipeline function. And this is basically going to go through and just automatically name things for us. So no list, no tuples, no anything like that. Just sort of, it's a time saver for you. As this will go ahead and make a pipeline for you without having to have you directly type in list, tuple 1, name of step, step, tuple 2, name of step, step. This will sort of just automatically name it for you on its own. A little time saver, doesn't need to be there right now. So it goes through and it kind of creates this pipeline for you. So this part is going to be kind of a little bit of a quick diversion, just because this is to help fill in some holes that exist in the scikit-learn library itself that are in process of being filled but aren't quite there yet. And this is to take care of some steps that scikit-learn isn't handling pretty well for us, right? And from what I've seen from catching up with different discussions, these are issues that you have also faced already as well, which is, what do we do if we have strings that are encoded, that are categories that are encoded to strings? How do we create dummy features for that? And what do we do if there are categories in our test set that aren't in our training set? There's a lot of different ways to handle this. Scikit-learn doesn't have a lot of elegant ways to handle it yet. They are upcoming. But what we're going to do is we're going to kind of sort of modify it. We're going to create a different class to kind of handle this for us. There is a library in scikit-learn called OneHotEncoder. We haven't really covered it yet, but what this will do is it'll take a column of data and convert it into dummy variables, one per unique instance in that feature, which sounds almost exactly like what we want, right? Basically, pd.getDummies. It's got a couple of options. It's going to default to putting out a sparse matrix. We'll make that into a true one, and it will try to yell at us if it sees something new that it's never transformed before. The problem with this library is that it only transforms columns that use integers. It doesn't do anything with strings. It will yell at you if you try to give it a string. There is a more user-friendly version of it called categorical encoder that is under development, but it's not out yet, and it's not quite clear exactly when that's coming out. So we're going to kind of go through here and just monkey patch something. And we're going to create a class that is going to take in a data frame. It's going to extract that column. It's going to assign a unique integer to that string. And then it's going to hold on to that so that if it sees new data, it can kind of say it's none of these. In the interest of time, I'm just going to define the class, and we're just going to move forward and use it. But this is a really good opportunity to go through and sort of kick the tires, investigate what makes this class work, try tweaking things and see what happens. This is not also rigorously tested, so it's not to the standards that scikit-learn's code is. So there may be chances that I haven't foreseen where it doesn't work. That's fine. We're just going to use it kind of right now until scikit-learn sort of gets their act together. So don't worry too much about what's happening here. We're just going to define and move on. But for those of you for whom like classes are kind of like familiar territory, pipelines are familiar territory, this is a good place to kind of come through and bonus work, try to figure out what's doing here. But what this will do is that we'll be able to have this new class called categorical extractor. We'll give it a dummy, we'll give it the column of a data frame, and that will get it set up so that OneHotEncoder can do things with it. So here, I'm going to give it sex. I'm going to pass that into OneHotEncoder, and it's going to create dummy variables for me based on those values that are already encoded to strings. So there, this output over here comes from line 6. It's columns for male, female, and juvenile. And we sort of see that kind of based off of here. Don't worry too much about the mechanics here. This is just kind of set it up so we can kind of use it within here as well. So yeah, cool. So let's talk about those parallel steps. You remember we talked about there are steps that we want to do in sequence, and there are steps that we want to do in parallel. And what we want to do, right, if you remember back to that pipeline object in that check for understanding, we sort of just looked at one column, and we kind of took that one column and just did steps 1 to 1, 1, 1, 1. We may want to do multiple steps to multiple different columns at once, right? I want to take the sex and extract it like this. I want to take the shucked weight and I want to do this with it. Then I want to take those results and put them back together. Feature union is what does that second part. And what feature union will do is it's going to take in some sort of fit and transform object or a pipeline, and it's going to take in a set of pipelines and do those steps at the same time versus sequentially. So what we'll typically do here is we'll make a pipeline. So here I'm going to take this pipeline, I'm going to extract petal length from the iris data set, and I'm going to pass it into Binarizer. And this is a pipeline that will do these two things. And then I'll make a second petal length, a second feature, which will take out the petal, that should be petal width. Sorry, I will slack out this updated code. It'll take that petal width, and it'll create polynomial features based on that, right? Here's that updated code. It's just changing the name of that column. So now I have two different pipelines, right? One pipeline looks for petal length and does something to it. One pipeline looks for petal width and does something to it. And what I'll do here is feature union will let me take those results. It'll take the result of each of those pipelines and then join them together. Now, just like that pipeline object, we're going to create a list of those of that with tuples, name of that pipeline, and that pipeline. So in this case, here's feature union, name a step, the step I'm trying to do, which is a full pipeline object itself, name a step, full pipeline object itself, and then I can call .fit on that data set. And what this is going to do is it's going to go through, it's going to take each of those pipelines that fed into it, it's going to do each of them in parallel and join the results back together into one place. And sure enough, if I run .transform, it's going to give me each of those things. And those features are going to be in order of the steps provided. So this first column is going to come from that petal length pipeline. Those second two columns are going to come from that petal width pipeline, because polynomial features is creating two features. And just like that pipeline object, make union will sort of kind of automatically name it for you, so it's a little easier to write out. So here I'm just saying, take petal length pipe, take petal width pipe, make a feature union out of it. And this will go through and just automatically fit and transform what that looks like. So okay, so we'll do another check for understanding. We'll sort of like we'll try out with these things. Use make pipeline and sort of create three different pipeline objects. Length with binarizer, diameter with polynomial features, and height with binarizer. Before you run it, think through and say, like, how many features is pipeline A going to make? How many features will pipeline B make? How many features will pipeline C make? Put them all into make union and fit and transform xtrain. And we'll take 7 minutes for this, because I kind of want to make sure that we have a lot of time for questions at the end. So we're going to cut down that time a little bit. Again, all the solutions are in that solution notebook. So if you do kind of get tripped up on one or two of these, we can go back and check that later. So let's get that going. And that'll be that second check for understanding about feature unions. Okay, cool. Let's keep moving. So if you did not get all the way through the feature union check for understanding, also fine. Again, that solution code exists, and we're going to sort of just take a lot of extra time to make sure that we are sort of following along. But what I want to do is Hong asked a really good question in the Slack, which is there any way to put these back to the data frame and then predict off of this? Because that's what we're typically going to do. And there is. And this is sort of the magic of pipeline and feature union. This is the sort of like real reason to do this. And that's because we can chain these things together. And as long as we can break down all the things we need to do for our feature engineering in our model into sets of steps that have to happen in parallel or steps that have to happen in a series, and if every step in those places has a fit in a transform method, we can map out that entire process and join it all together using this pipeline and these feature union objects. So what I'll do is I'll walk through like a really quick example using this abalone data. And my model is going to do the following things. It's going to need to transform data in parallel. So it's going to go through, it's going to extract sex, it's going to create dummy variables. It's going to extract length and not do anything else. It's going to extract width and not do anything else. And it's going to extract diameter and create polynomial features. So that's 2 different transformations and 2 different pipelines. We're going to feed that into a feature union, which will join them all back up together into a big old NumPy array. Then it's going to scale those values, and it's going to fit them into a random classifier, a random forest classifier. So we're going to have a feature union, which has different pipelines inside of it, inside of a pipeline that sort of walks through this. So we'll kind of walk really slowly through this code, but this is where the magic of these 2 libraries comes together, which is we can join these things together and sort of, almost like Legos, create different steps until we have the sort of pipeline that we're looking for. So first thing I'm going to do is I'm going to create these 2 sort of multi-step extractors, right? These are going to be the things that are going to have, they're going to work on individual columns, and going to do more than just take it out. So here, we're going to grab that sex column. We're going to encode it into dummy variables. That's one step, right? Take sex, create dummy variables. One set of serial steps. The next is take diameter and create polynomial features. Again, we're going to, that's one set of series of steps. So I'll run that. So now I've got 2 pipelines. The next thing I want to do is think through that sort of first step, which is do all these things to the columns at once and put them back together into one full data frame, or one full sort of NumPy array. And that's what this is going to look like, right? Here's my make union, which is going to take in a bunch of steps that have fit and transform methods and do them in parallel. So take extract sex, so get my sex columns, get my length columns, get my height columns, and get my diameter pipeline. Do all these things in parallel and put them back together. The thing that makes this work is make union, so feature unions and pipelines also have fit and transform methods. So they can be part of other feature unions and other pipelines. So my main modeling pipeline, right, which is the thing that I'm going to feed my original data into, is go and take this data, do all the transformations to it, put them all back together, scale that set of data, and then pass that into random forest classifier. And so here it is, right? Here's my pipeline. Feature transformers is that feature union we've just defined up above. Standard scalar is we've seen standard scalar before. It takes in an NumPy array or data frame and scales it. And random forest classifier takes in an NumPy array and creates a random forest for it. So we'll run this. And then finally, now this modeling pipe acts like a random forest classifier, but also does all the transformation and splitting up and binning and feature extraction that we need in this pipeline as well. So what this takes in is not the clean, ready-to-go data. This takes in the raw, dirty data and fixes it for us before we test it, before we even run the model. So we'll fit here against this training data, which is great. It's all done. We can kind of look through all those steps, and we'll score it against that training data. And that did pretty well. And we can also score it against that test data. Again, because it's going to look just right at that raw data and just do all the transformations for us, extract those columns, do all that work in parallel, join them back together, feed it through scalar, feed it into random forest. And we can even kind of go through here. Here's just that, that confusion matrix and that classification report. And it'll actually kind of come through here and show us what that looks like. This is the real power of pipelines, right? to be able to say, okay, here are the steps I want. I want some sort of feature extraction step here on line 2. I want to scale the results of that feature transformation step on line 3. And I want to take that data and I want to put it into a random forest classifier on 4. What does feature transformers look like? That's going to be a feature union of different pipelines or different fit and transform objects, each working on an individual column itself. All right, cool. So because I want to keep you all coding, we're going to work until 12 p.m. Central, 1 p.m. Eastern on this last check for understanding. And then we're going to really kind of go through here. And I'm going to kind of have a lot of time for questions because I know there's a lot of extra steps that we're kind of probably missing here. So your goal for the next 15 minutes is to try to take this model that I've made and make those predictions more accurate. How you choose to do so is up to you. But you have to put all your changes into this pipeline sort of thing. So you can modify that feature transformers portion to add in more features or change how they're transformed. You can change the type of model. You can change the hyperparameters that are in the model. I put all the code from above into this section right here. So all you have to do is kind of come in here and modify these things, the steps that go into that pipeline, to try to make your predictions on that test set better than they already are. So cool. So we'll take 15 minutes. We'll work on that, and the rest of the time is going to be to wrap up and sort of have a lot of time open for question and answers. Talk about the why, the what, how this works, where it works. My suggestion for the check for understanding is to make really, really small changes. Try adding in one new feature extraction pipeline or one new feature first, and sort of build out from that. So cool. Let me give you all 15 minutes for that, and we'll sort of check back in to wrap up, talk about conclusions. And sort of get you all ready for the lab after that. See you all on the other side. right, we've got about 30 seconds left. I'm going to start sort of walking through my conclusion. We've got essentially as much time as we want to spend on questions and answers at this point. So like really do sort of think through what was clear, what wasn't clear. Big, broad, general questions are also super okay. This is not particularly easy stuff. It's very big conceptually. It's a very different way of thinking, especially if you've never seen this stuff before or thought about this stuff in this way. It's quite tricky. So I'm seeing a lot of 2s in that little poll that I put up there, which is almost exactly where I wanted students to be at this point. So if you put down a 2, you're where you should be. This is for exposure. This is to kind of get you thinking about what's happening under the scenes. You know, the chances that we'll walk away from here like masterfully applying this stuff is going to be a little less than expected. You'll have a lot of chances this afternoon in the lab to sort of apply this yourself, because we're using the same data from Project 3 that we've seen before. We'll sort of think through what that looks like. So there's a questions thread in Slack. So please, as I like sort of wrap up, think through and talk through like what you've seen and what you're interested about, and we'll sort of wrap up here. In conclusion, right, pipeline and featuring can really create these kind of robust and powerful ways to systematically and reproducibly transform and predict these models, right? It packages all these steps up that we need into one single command. And one of these development principles that we've talked about before is DRY, right? Do not repeat yourself. And this is very explicit in that once it's said, you're not going to repeat yourself. You can't. So it's explicit transformations that go into there. Everything that happens to that training data will happen to that test data once you use this pipeline. It puts it all up in one command, and that reduces the chance that compared to doing things manually, us doing things in the wrong order, forgetting to transform this feature or include that one or that sort of stuff, won't error out, right? And this is great for us. I am an incredibly distrustful person myself. I will mess things up given half a chance. So having things like this set up where the less input I have into the process, the better, is really good. That means that things are robust. They'll run without my constant like tweaking, and that's a really good thing. This sort of structure means that pipelines are usually kind of in this refactoring, finishing up step, right? This is where we're saying our model's good to go. I'm happy with this. I'm going to rewrite this so that no matter what new data I see, it'll pass through and predict things. It's a deployment thing. It's a refactoring thing. If you're starting off with a new model, if you're starting off with a new data set, don't worry about pipelines. That's a later on down the line step. Now there is one extra part, and I kind of want to just point this out and then walk away from it. There is an extra section that follows this about applying grid search to a pipeline. And this will let you tweak a lot of parameters that happen than just the one hyperparameter of a model. You can put in different models and test those. You can put in different features, different sets of pipelines, all of that sort of stuff. This can be a really good way to sort of kind of automatically try a bunch of different things at once using grid search. We're not going to dive into that right now because it's sort of a much more advanced topic. But if you put down maybe a 4 or a 3 and you're feeling really confident about this, go through and take a look at that. It should be pretty illuminating into some of the other things that are happening here. OK, taking a step back, go ahead and if you have any questions, put them in the Slack. We'll start sort of working through them. Big, broad, like why do we even learn these questions? Absolutely good. Small, sort of detailed questions, also great. Put them up there. I'm going to answer Hong's first because she put that in the thread, which is basically, if I can open that up. What would you want to do if you wanted to extract 100 columns, run a for loop, and add that to a make pipeline list? That's certainly one way that you could do it. There's a couple of other questions. So it's one of these things where, again, we kind of want to really think through what are the tools we're using and how are we using them. If we want to take 100 columns that are in our data set and just apply them like that, that might be a case where we create a new extractor class that says, you give me a list of columns, and I'll give you out the full set of them as one step. Or maybe before we start, we just like limit out those columns ahead of time. It's going to be a balance between like what is the easiest thing to do versus like what should be kind of explicitly put out in that pipeline. I have done things like that before where I've said, here's my like custom class. It looks for the last 100 columns and just takes those and puts them into the model. That's also a way to do it. So a couple of questions pop up. What's really great about this is that it sort of relies on those lessons before about what classes are, what objects are, certain methods that are sort of carried through and followed through with those things. Those are the big picture classes and objects that underlie a lot of development work overall. And then we're going to use those, and we have used those in this example, to sort of create our own custom cases for a pipeline model object. I'm not seeing a ton of big questions. So nobody's typing, nobody's doing anything. So I'm going to assume that either you are good to go and ready to be let out or not. You guys can always PM me with any questions that you have about both like the code for this and also sort of bigger, broader questions around here. To look ahead a little bit to the lab, just to kind of give you that sneak peek. Come on, internet. You got this. Lab OOP. There we go. So today's lab is kind of interesting. And what we're going to ask you to do is, it's very open-ended. We want you to create a new notebook within this repo, grab that train.csv file from project 3, pick out either the regression or the classification challenge, do a train test split on it, look at the code you're writing for project 3 right now, your regression, your classification challenges, and pick at least 3 of those columns to include in this version of the model. And refactor what you've done for project 3 using pipeline and feature unions to do the same thing. It's not part of your project 3 submission, but it's a chance to kind of use that material and investigate stuff while you're practicing these models. You don't have to refactor the entire model. You don't have to refactor the entire data transformation. You don't have to submit it to Kaggle. Just use what you've already done for project 3 and just sort of like reapply it using pipelines as opposed to the code that you have already. It's fairly short. This is so that you have more time to work on project 3 if you need it. But having one pipeline object with 3 features is all we're asking for. If you want to take that into more, that's great. Hacking away at the scikit-learn library is a great way to become familiar with it. And just in case you need those that extra code, I've kind of included that feature extractor and that categorical extractor code from today's lesson. All right, I'm not seeing anybody bound on my door for questions. So yeah, I will let you all go. Thank you all for your attention. Tomorrow we're going to talk about hierarchical clustering and how to evaluate whether clusters are well-formed or not well-formed. So I'll see you all then. Have a good lab, and looking forward to your project 3 submissions tomorrow. Bye.